Okay, Chem, today we're going to talk about the other way, not across, but down a family or a group, which would be the columns on the periodic table of the elements. Remember, when you're in the same column on a periodic table of the elements, you have similar chemical properties due to the fact that you have the same number of valence electrons. What causes the properties as we go down is not the Coulombic effect, which is the increased number of protons in the nucleus, but the same valence electron shell. This time it's called the shielding effect, because as we go down, we have increased number of electron shells. So this time my nucleus is going to be tiny, tiny, tiny in the center because we're not going to focus on the nucleus now. We're going to focus on the principal energy levels. So here is the N equals 1, N equals 2, N equals 3, and N equals 4. So N equals 1 is hydrogen and helium. Hydrogen and helium are in the first principal energy level. But let's just deal with family 1. That's our alkali metals. The alkali metals have 1 valence electron. Remember, hydrogen is stuck with them, kind of stuck in that family because he has 1 valence electron, but he is a nonmetal. But let's start with hydrogen. He's in the first principal energy level, and he has 1 valence electron there. Now let's go to lithium. Lithium has 3 electrons, 1 valence electron in the second principal energy level. Now, hydrogen is small, super small, because he is not shielded. His valence electron is not shielded from the pull of the protons in the nucleus by full electron shells. Lithium is a little bit bigger because his valence electron is shielded from the pull of the protons in the nucleus by the full N equals 1 first principal energy level. So the first principal energy level, the first full electron shell, shields lithium's valence electrons from the pull of the proton in the nucleus. Okay. Let's go down to sodium. So sodium has a second full shell. So he has the first full shell still, and he has the second full shell. The N equals 2 shell is full. And then he has 1 valence electron in the third principal energy level. The pull of the protons on this valence electron is shielded by these 2 full electron shells. So the pull of the protons on the valence electrons is shielded by the full electron shells 1 and 2. Therefore, he pulls on them with less energy, with less force, and it is easier to pull that electron away from him. It is also responsible for the fact that sodium is larger than lithium or hydrogen. So as you go down a family, the electronegativity decreases, the ionization energy decreases, and also the size increases or atomic radius increases. So let's fill up the third principal energy level. 1, 2, 3, 4, 5, 6, 7, 8, and talk about potassium. Potassium is in the fourth principal energy level. He has 1 valence electron in the fourth principal energy level. This time, there's 3 full energy levels shielding this valence electron from the pull of the protons in the nucleus. So this causes potassium to be larger. It also causes him to have a lower ionization energy than sodium. It causes him to have a lower electronegativity than sodium. So as we go down the family here, they start to get larger. The trends are the radius increases as you go down. The electronegativity decreases. And the ionization energy also decreases. What that means is that potassium is the largest, and he has a smaller electronegativity, and he has a smaller ionization energy. This is all caused by the shielding of the protons in the nucleus. This is what we're talking about when we're talking about chemical reactivity. So if we go all the way down to francium here, we're going to put another star in this corner. Remember, we already put a star on fluorine after ignoring the noble gases. But fluorine is the largest metal. I mean, not fluorine, francium. We're down in metals here. Francium. He would be the largest. He would have the smallest ionization energy, and he would have the smallest electronegativity. This makes him the most chemically reactive metal. It also makes him the most metallic. It also makes him extremely dangerous also. If you notice, his mass isn't even, it's in parentheses down there. The reason it's in parentheses is because he does not stick around long enough. His valence electron flies off so quick they can't even get a mass of him because he's that reactive. They cannot find him by himself ever. And that is a summary of the shielding effect, which is caused by the full electron shells shielding the valence electrons from the polar protons in the nucleus. All of the trends going down a family are caused by the shielding effect. So remember, shielding effect is from top to bottom of a family. Coulombic effect is from left to right across a row or period.